Hello, adventurer. Welcome to SCARTHQuEST. This is our first podcast made using Notebook LM audio overview. I hope you love the video and learn listening to the audio just like me. So let's start our podcast with our host.
For a second, or your laptop, whatever you're using to listen to this. It feels seamless, right? You tap an app, it opens, you type a message, it sends, it feels so fluid. But if you actually stop and think about what is happening under the hood, it's terrifyingly complex.
Oh, it is. We're talking billions of operations a second. It's overwhelming if you try to hold it all in your head at once. It borders on magic.
Right, it feels like magic.
Yeah.
But the premise of this deep dive is that if you zoom in, and I mean really zoom in, past the sleek glass screen, past the software code, all the way down to the raw silicon, the magic completely evaporates.
It does. At that level, there is no magic. There isn't even math in the way we usually think about it.
No calculus, no complex geometry.
None of that. At the absolute foundation of our digital world, there are just millions upon millions of tiny switches asking incredibly simple yes or no questions.
And the rules for how those switches talk to each other. That isn't modern computer science.
No. That is 19th century philosophy.
Which is where my brain starts to hurt. We are basing the entire modern internet on the work of a guy from the 1850s who didn't even know what a light bulb was, let alone a smartphone.
It's one of the great ironies of history. So today, we're doing a deep dive into Boolean algebra. We're going to look at the logic behind the machine.
The DNA of every computer circuit in existence, essentially.
That's a great way to put it.
We've got a stack of sources today, primarily centering on a heavy text regarding digital fundamentals and logic simplification. Our mission is to figure out how we get from, abstract philosophy scribbled on a chalkboard in Victorian England to the chip inside your phone.
And, more importantly, why simplifying that logic is the only reason your phone doesn't melt a hole in your pocket.
You're not kidding, are you?
That is a very literal risk, by the way. But to understand why, we have to go back to the beginning, to George Boole.
The man, the myth, the logician, 1854.
1854. He publishes an investigation of the laws of thought. Now, I love that title, The Laws of Thought.
It's very grand.
It is. And he wasn't trying to invent electronics. He was trying to come up with a mathematical way to describe human reasoning.
So he wanted to turn thinking into algebra.
Precisely. He proposed a system where every variable, every thought, could only have two states, true or false.
And this is where the history gets weird for me. Because he publishes this, and the world just goes, cool story, George. And then nothing happens for almost 100 years.
Basically. I mean, it was an academic curiosity. It was philosophy, math. It just sat on the shelf because there was no machine that could actually use it.
Until 1938.
Until 1938. Enter Claude Shannon.
Ah, okay.
The unsung hero of the digital age. Claude Shannon is a master's student at MIT. He's working with these clunky electrical relay circuits, big mechanical switches that click open and closed.
Right.
And he has this light bulb moment. He realizes that a switch is binary. It's either open, which means no current flows, or it's closed, and the current flows.
So open is false, or 0, and closed is true, or 1.
Exactly. He realized that Boole's 19th century true-false philosophy mapped perfectly onto 20th century on-off electricity. Shannon was the bridge. He proved you could use Boole's algebra to design electrical circuits.
That is a heck of a master's thesis.
Oh, it's arguably the most important master's thesis of the 20th century.
I'm just going to invent the foundation of digital logic, no big deal. Okay, so let's get into the actual meat of this.
Yeah.
If we want to understand how our devices think, we have to learn the language.
Right.
In normal algebra, the stuff that gave me nightmares in high school, you have variables like x and y, and they can be anything, 5, 100, -42.
Right. Infinite possibilities.
But in Boolean algebra, the rules of the game are strictly limited.
Very strict. In this world, a variable, let's call it A, represents a condition. In a physical computer, that condition is a voltage level, high or low, but logically, it's just 1 or 0.
There is no 2. There is no 1.5.
No gray areas. It is a binary world, and alongside the variable, you have its evil twin, the complement.
This is the A bar in the text.
Right. Written with a little bar over the letter, it just means not A. It's the inverse. If A is 1, not A is 0.
And if A is 0, not A is 1.
You got it.
Okay, I'm with you so far. Toggle the switch, on or off. But then the text gets into Boolean addition and multiplication, and this is where my intuition drives off a cliff.
I know this part.
Because the text says Boolean addition is the same as the OR operation.
Correct.
But then it gives the rule, 1 + 1 = 1, and my math brain screams 2.
It does, I know. But you have to stop thinking about numbers and start thinking about switches. Let's make this physical.
Okay.
Imagine a simple circuit with a light bulb and a battery. Now imagine 2 switches installed side by side on the wire. This is a parallel connection.
Okay, so the electricity can go through switch A or switch B to get to the light bulb.
Exactly. If you close switch A, which is logic 1, the current flows. The light turns on, logic 1.
Got it.
If you leave A open but close switch B, also a logic 1, the current flows through the other path. The light turns on.
Okay, makes sense.
Now, close both switches. Switch A is 1, switch B is 1. Does the current flow?
Yes, of course.
Does the light bulb turn into a supernova? Does it get double bright?
Oh, no. It just turns on.
That is why 1 + 1 = 1. The condition is the path complete. If both paths are complete, the answer is still just yes.
Okay, that actually makes sense. It's not summing up apples. It's checking for a pathway.
Exactly.
So that's addition or the OR gate. What about multiplication? The text says that equates to the AND gate.
Right. Now imagine those 2 switches aren't side by side. Imagine they are in a series, one right after the other on the same wire.
Okay, so the electricity has to pass through A and then through B.
Exactly. If I close switch A, but leave switch B open, 0, does the light turn on?
No. The wire is still cut at B, so 1 × 0 = 0.
Correct. And if I close B but not A?
Still dark. 0 × 1 = 0.
The only way to get a 1
is to close A and B. 1 × 1 = 1.
Precisely. That is the physical reality of the AND gate. You need all inputs to be high to get a high output.
See, when you put it that way, switches on a wire, it seems incredibly simple. But then we get to the laws, and most of them are the standard stuff. Commutative, associative. Basically, order doesn't matter. AORB is the same as BORA.
Right. Those are the comfort food of algebra. They work exactly how you expect.
But then we hit the weird rules. The text calls them rules of simplification. And this is where I feel like George Boole is trolling us.
A little bit, yeah.
Let's look at Rule 5, A + A = A.
The idempotent law. But again, think physically. You have 2 switches in parallel, an OR gate, but they're both controlled by the exact same input signal, A.
So if I flip the switch for A, both paths close at the exact same time.
Exactly. So having 2 of them adds absolutely nothing. It's redundant. If A is on, the light is on. If A is off, the light is off. You might as well just have 1 wire.
So if I see AORA in a formula, I can just cross 1 out.
Yes. And that is the first step in simplification. Getting rid of the junk you don't need.
Okay. How about Rule 6? A + A bar = 1. A variable ORed with its own opposite is always 1.
This is one of the most philosophical rules. It's the law of the excluded middle. Think about it. A is a condition. Let's say A stands for it is raining. Then not A means it is not raining.
Okay.
So the statement is it is raining or it is not raining. When is that statement true?
Always. It's got to be one or the other.
Exactly. There is no middle ground. One of those paths must be closed. So logically, the result is always a constant 1, true.
Meaning if I see that in a circuit design, I can just replace that whole mess of wires with a permanent connection to the power source.
You got it. You just saved yourself some components.
Okay, now let's look at the heavy hitters. The rules that actually let engineers take a chainsaw to a complex design. Rule 10, A + AB = A.
The absorption rule. This is a big one.
It looks wrong. A + AB. You have an A and you're adding an A times B. Shouldn't the B matter? But the rule says the B vanishes.
Let's break it down logically. The expression means this output is true if condition A is met, or if condition A and condition B are met. Scenario 1. Condition A is true. The first part of the OR statement is satisfied. The output is true. Does it matter what B is doing?
No, because in an OR gate, you only need 1 true.
Right. Scenario 2. Condition A is false. The first part is false. Now look at the second part, A and DB. If A is false, can A and DB ever be true?
No. Because an A and D gate needs both. If A is 0, the whole A and D term is 0.
Exactly. So if A is false, the whole thing is false. If A is true, the whole thing is true. The variable B has absolutely zero impact on the outcome. It is logic clutter.
So B is just along for the ride.
It's a parasite. It's consuming power, taking up space, and doing nothing. Rule 10 gives you permission to delete it.
That is surprisingly satisfying. Okay, one more rule before we move on. Rule 11. A plus A bar B equals A plus B.
This is a variation of the same idea. If you have AOR, not A and DB.
The rule says we can just drop the not A.
Think about the only time the second term, the A bar B, matters. The second term is only relevant if A is false or 0.
Right, because if A was true, the first term handles it.
Exactly. So if we are looking at the second term, we already know A is 0, so A bar must be 1. So the term really just depends on B.
So you're saying the not A is redundant context.
Exactly. It simplifies to just A or B. This allows engineers to eliminate an inverter and an A and D gate connection. It makes the circuit cleaner.
Cleaner is a nice way to segue to the next section, because sometimes you don't just want to simplify, you want to rearrange. The text brings up De Morgan's theorems.
Augustus De Morgan, a friend of Boole's.
And his theorem has a mnemonic that sounds like a dance move. Break the bar and change the sign.
It does stick in your head, though.
Explain this to me. Because visually, we are talking about a big horizontal bar drawn over a whole equation, right? Like A and DB, all under one roof.
Right. A big bar over everything acts like a giant not sign. It means the inverse of A and DB. This is what we call a NAND gate, not AND DB.
Oh, okay. And De Morgan's trick is to break the bar.
Imagine snapping that long roof in half. One piece falls over the A, one piece falls over the B. So now you have not A and not B.
But the second part of the rule is change the sign.
So the A and D becomes an OR.
So not A any B is mathematically identical to not A or not B.
Precisely.
Why do I care? Is this just shuffling deck chairs?
No, this is crucial for manufacturing. Let's say you are Intel or AMD, you are building a chip. Sometimes it is incredibly cheap to print millions of NAND gates. It's just how the silicon is etched.
Okay.
But your logic design calls for a negative OR gate. De Morgan tells you, hey, these are the same thing. You can use the cheap NAND gates to build any logic function you want. It gives you flexibility.
It's like a chef realizing that if they run out of buttermilk, they can mix milk and lemon juice, and it does the exact same chemical job in the pancake.
That is a perfect analogy. It's a recipe substitution for engineers.
Okay, we've covered the building blocks, the weird rules, and the recipe swaps. But I want to talk about the so what. Why do we force electrical engineering students to do pages and pages of this algebra?
It's not just hazing. It comes down to one word, efficiency. But in computing, efficiency means something very physical. It means heat.
Heat?
Every time a transistor switches, it uses a tiny bit of power and releases a tiny bit of heat. One transistor, no big deal. But a modern processor has 50 billion transistors.
So if you have extra gates,
If you have logic, clutter, unnecessary gates flipping on and off, you are generating waste heat. If you didn't simplify the logic, your phone wouldn't just run out of battery in 10 minutes. It would literally burn your hand.
okay, that puts in perspective.
Yeah.
Let's walk through a concrete example from the text to see how this works. Example 4 to 9. I'm looking at this equation, and it's a beast.
Leone.
It is AB plus A times B plus C plus B times B plus C.
Oof. Okay, visualize that. You got an A and DB gate, then you've got an OR gate for B and C, feeding into an A and D gate with A. It's a mess of wires.
A real tangle.
If you built that, literally you're looking at, what, 5 or 6 logic gates?
At least. So how does an engineer attack this?
Step 1, distribute. Get rid of the parentheses.
That's high school math. So A times B plus C becomes AB plus AC.
Right, and B times B plus C because B plus BC.
Okay, stop there. BB. B, A, N, D, B.
Remember our rule. B times B is just B. So that term simplifies immediately.
So now the equation is AB plus AC plus B plus BC.
And we have 2 ABs, AB plus AB.
Right, A plus A is A. So
Yeah.
AB plus AB is just AB.
So now we are down to AB plus AC plus B plus BC. Look at the terms of the B. We have a plain B and a BC.
That's the absorption rule. Rule 10, B plus BC. The BC is redundant logic clutter. The bee eats it.
Exactly. And look again, we also have an AB.
Oh, right. We have a B term and an AB term. The bee eats the AB too.
Boom. So all those B terms, the AB, the BB, the BC, they all just collapse into a single B.
So what is left standing?
Just the B and that lonely AC term we haven't touched. The final answer is B plus AC.
Wait, we started with that giant string of characters, and the answer is just B plus AC.
2 gates. We went from a 5 or 6 gate monster down to 2 gates. An OR gate and an AND gate.
That is massive.
That is 60% less silicon, 60% less power for that specific circuit, 60% less chance of a failure. That is why we do the math.
It's incredibly satisfying to watch it shrink. But I imagine doing that line by line for a huge chip is tedious. The text mentions a tool that makes this visual, the Karnaugh map, or K-map.
Oh, I love K-maps. This is where we leave algebra and enter the world of pattern recognition.
Describe this for me, because in the book it just looks like a grid.
Think of it like a game of Battleship.
Battleship, okay.
You have a grid. On the top, you have your input variables for columns, like 0, 0, 0, 1, 11, 10. On the side, you have your rows. Every square on that grid represents a specific combination of inputs.
So the top left square might be A is 0, B is 0.
Exactly. Now, instead of writing a formula, you look at your truth table, which tells you what the answer should be, and you plot the ones, the trues, onto the grid. You place your battleships.
So I have a grid with a scattering of number ones on it.
Now here's the magic. You look for islands of ones, you look for adjacent groups, a pair of ones side by side, or a block of 4 ones, or a row of 8.
And if I find a group?
You circle it. And that circle tells you something profound. Let's say you have a group of 2 ones side by side. As you move from the left square to the right square inside that circle, one of the variables changes, say, from 0 to 1.
Okay.
But the output stayed 1 for both.
Oh. So if the variable changed but the output didn't,
Yeah.
that variable doesn't matter.
Exactly. The K-map visually shows you which variables are irrelevant. You don't have to do the absorption math. You just circle the group and say, oh, variable A changed, but the light stayed on. Cut variable A's wire. We don't need it.
That is brilliant. It turns calculus-level simplification into a find the shapes game.
It capitalizes on the fact that human brains are excellent at spotting visual patterns. It's a cookbook method to getting that minimum expression instantly.
So we have gone from George Boole's philosophy to Shannon realizing switches are logic, to the math of 1 + 1 = 1, all the way to playing Battleship to design the chips in our iPhones.
It is quite a journey, and it really reinforces that the digital world isn't built on magic. It is built on rigorous, ruthless simplification.
I want to linger on that thought for our sign-off. Ruthless simplification. We talked about how A plus AB equals A. If you have the core thing, A the extra condition, B is just clutter.
Logic clutter.
I feel like we all have a lot of logic clutter in our actual lives. We act like we need to do A and B to be successful or happy or productive.
Right. I need to go to the gym, A, and D, I need to have the perfect workout outfit, B.
Yes. But logic says, if you go to the gym, A, the outcome is achieved. The outfit B is absorbed. It's irrelevant.
That is a great application. The B term is just draining your mental battery.
Exactly. So that is my challenge to you listening today. Look at your to-do list. Look at your worries. Find the NDs that are just masquerading as requirements. Apply Rule 10, delete the clutter, and save your energy for the stuff that actually keeps the light on.
Simplify your circuit.
Thanks for deep diving with us. We'll see you on the next one.
I hope you enjoyed the podcast made using Notebook LM. I really wanted to share the experience of learning stuff by listening to the podcast, and that's why I made this video. I hope to bring similar ideas to this channel, but yeah, I will be giving my main priority to my main series that are Math from Scratch series and Computer from Zero. But I will also doing some side ideas, side things, so learning can be fun and free. So yeah, hope to meet you on next video. Bye bye, tata.